So again, so it's on the tape. If you want to take the test on Friday, send me an email. At this point, what's exactly on the test will somewhat depend on what we get to today and Monday. So as usual, you'll remind me Monday if there's anything on the review that you can ignore. So we'll get to that. So it's a little early, but any questions about the test? We'll really deal with this next week, but I haven't looked at it too much. I forget exactly where test 1 ended. I think we did the one Markov chain, but we didn't have the fixed vector yet. So I think that, along with getting the time to go from one state to another state, was not on it, which means it is on this, and that was the first thing. But for next week, I'll look more exactly, and I'll let you know what's actually on it. And if you look at the review, you can see that what's on it. All right, so as I said, the last couple classes, we've done a bunch of new things. We've done the stock, we've done the Brownian motion, and yesterday we did the Black-Scholes stuff. So let's start off this class with just doing one of each. So start off with the basic stock one. So the basic simple one. So we have a stock that is currently at $100, and in the future it's either going to go down to $75 or go up to $250. We also have an option to buy the stock at $125. If I let P kind of randomly be the probability that stock goes down to $75, I want to find C, the price of the option I should charge so that there is an arbitrage. So for this, we know from the arbitrage theorem that either there's always arbitrage or there are values of P and C that will make both the expected value equations equal to 0. So we have the expected value for stock. What is the expected value for stock? And this is just kind of a basic expected value times probability. So what do I multiply by P? What are the numbers that go in front of each of these? P and 1 minus P. So in front of P is negative 25. And in front of 1 minus P is just 150, because here we're just doing stock. And here I might as well solve it, since this only has the one variable. I can solve it as it is. So I need that to be 0 for some P. And so if I bring everything over, I get 150 is equal to 175p. So therefore, P is equal to 6/7. As I stated in the beginning, that probability doesn't really mean anything. It's just saying that there is some thing that can happen, which means we can't have arbitrage. Same thing for the option. And again, there are the two possibilities. And again, let me ask, what are the coefficients for each of those for this one? So for P, the coefficient is what goes in front of the P. Yeah, so negative C. And what goes in front of 1 minus P? So you're just missing the little thing, which is it's 250 plus the 125. Because what's going to happen is we would buy it for $125, me sell it for $250, and therefore we make $125 minus whatever we had to pay for the contract. And this also we need to be equal to 0, assuming that there's a solution. And we solve that. So if I multiply it out, if I bring the C to the other side, I get that. And so I should charge about $17.86 for the option. Okay. So here's the base one. Any questions on this? There's the second way of solving it, but you don't really want to. This is the easier way. To check to see if you can actually set it up the other way, I could give you a different value of C. So if C is equal to 17.86, there is no guaranteed arbitrage for any other number there is. So the part B will be, if C is equal to some other number, give me values of X and Y that guarantee that you make money. So let's make it 5. So I'm charging $5 the option, and there's going to be guaranteed arbitrage. And if I let X be the number of stock I either buy or sell, arbitrarily will make positive buying and negative selling. Then what are values of X and Y that guarantee that you make money? So similar to the last one, we're going to get the two equations, except now we're going to do it by what the stock goes to and get what is the net amount I make. And pretty much the coefficients are the same as the last one. Just rearranged. So for this one, what is the coefficient for X? And so this is just the stock. So if the stock was $100 and now it goes down to 75, then I've lost 25. And if I have an option, it's now worthless and set minus CY. So notice the two coefficients here are the coefficients in the first column of the equations from the last one. And of course, we know C. So this top one, I'm not sure why I didn't simplify it, becomes minus 25x minus 50y. So I get that. So here there are kind of two ways of doing it. And if I do ask this on the test, you can do it whichever way you want, which means you probably would do it by just arbitrarily choosing numbers. So the two ways of doing it are solving it in general by doing the system of inequalities, so draw the graph, and the other is just trial and error. So what are values of x and y that will make both of these positive? In some ways, if you're doing trial and error, it should be obvious from the first equation that you want to make x negative. So for example, just make it simple. If x is negative 1, then I just need, for the second equation, I just need y to be big enough so that it gets bigger, and so that works. So if I put it into the two equations, in the top equation I get 25 minus 10, which is 15. If I put in the bottom one, I get negative 150 plus 240, which is 90. Both of those, of course, are positive numbers. That works. So if I'm just asking you to get any, and you do it arbitrarily, obviously there are an infinite number of possible answers. So you just have to make sure it works. So that's the first type, since we did the Q's. Any questions on this? All right. So the second type is Brownian motion. In some ways, this is not likely to be on the test just because it's built into the next problem, which is geometric Brownian motion. But there's no reason it couldn't be there as a standalone problem. So let's find kind of basic one. So the reason we can do this is we know that Brownian motion is a normal distribution because essentially you're adding up a bunch of distributions. So the central limit theorem tells us it's normal. And since it's the basic random walk where it's equally likely to go left or right, the mean is going to be 0. And in this one, in this part of it, we have made it so that the variance is equal to sigma squared times t. So in this particular case, it is 20. And now at this point, you have the two options. Since it's normal, we can either standardize this by subtracting this 0 from 7 and then dividing by the standard deviation, or I can go straight to calculator. So we want to go from 7 to infinity, so just put in a big number, put in the mean, put in the standard deviation. And we want the CDF. The PDF would just tell us what the height is at that point, which we usually don't care about. Actually, we never care about. So that I get 0.059. As always, the arithmetic part you should check. So there's basic Brownian motion. It's just a normal distribution where you know what the variance is. Or, of course, you can remember that as the standard deviation, just plug it in. So here's the basic one. This is the more elaborate one, which uses all the little notes that we have for Brownian motion. So the first thing, and I'll combine this into two pieces, into one, is so we have two distributions here. What do we know about those two distributions that will let us do this problem more easily? They're independent? Yes. So since the intervals don't overlap, they're independent. So if that had been b of 4 minus b of 1, we wouldn't be able to do the problem. We would need more background material. Second piece that we use is in terms of doing, so that means I'm going to be able to do these separately. What can I do with this one? How can I simplify that? What is the distribution for b of 2 minus b of 1? Right. And then the same thing with this. This would be b of so therefore, this comes down to, this is equal to the probability that b of 1 is more than 2, multiplied by the probability that b of 9 is less than 9. And pretty much, we can again just use the normal CDF, which means all we need is what is the variance for each of these, and then we'll plug it in like we did above. So for this one, the variance is again the sigma squared t. So sigma squared is still 4, and here t is 1. So this is 4. And in this one, it's again the 2 squared times, in this case, 9. So in this case, it's 36. and plug it in where we use the standard deviation. So the number up to infinity for the first one, negative infinity to the number second one because they're less than, and then the mean is 0, and the standard deviation is square root of the variance. And when I plug it into a calculator, I get that. This one you definitely should double check my arithmetic because I'm doing 3 things, getting each one separately and then multiplying them. So pretty much that's about as elaborate as we can get. So those are the 2 main types, a really basic one in A, and then one where you have to use the few different properties of Brownian motion. So any questions on this? Okay. So next example, and I'll do 2 of these together. So if we can assume that a stock can be modeled by geometric Brownian, which I'll remind you what that is in a second, and we know shortening things here, that the current price of the stock is, say, $50. The drift parameter, so let's say mu, is 0.03. The sigma is, say, 0.06. A is 0.04. And let's assume we have an option to buy the stock for $60 in 4 years. So let me remind you all things are here. The mu 0.03 is the drift parameter. The sigma is a measure of the volatility. So the bigger that is, the more the stock jumps up and down. A is the inflation rate. And then just this option, which we're not going to use for part A. 2 types of questions that we have done for this. One is doesn't use that last bit. Oh, I'll put this in a second. So let's find this. And this we're assuming this is the model. This is geometric Brownian motion. And again, what that assumes that the percentage change for each day are independent, and they're coming all from the same distribution. And you can see this is similar to the last problem with some algebra added in. So plug in all the numbers. And the extra algebra is what we want to do is now solve this for B of 3, because once we do, we can use what we did last time. And you see this is an exponential equation, so you're going to divide through by 50, take the natural log, and then solve for P of t. Oh, so for this part, we're ignoring this one. So I'm not asking about options whatsoever. I'm just asking about the price of the stock. So it doesn't matter when we can buy the option because we're just asking about the stock. And here I just kind of arbitrarily make up that we're looking at time 3. So that I would have to give you. Oh, that last number 3, that's 1.539. And so at this point, this is now, we've now made it like the last problem. We just need to know what's the variance. The only little thing here is, for this model, the variance of B of t is equal to just t. As I said, the idea is with stock, sigma measures the volatility, so that's something we can actually get. So we kind of pull it outside of the B of t to emphasize that number. So here, the variance is equal to 3, the value of t. So therefore, this is normal CDF 1.539, comma, infinity, comma, 0, comma, square root of 3. It's smoothing out all my lines. Sorry about that again. And I get that. 1.539. Sorry about that. Yeah, correct. 1.539. As I said, in some ways it's nice. It's smoothing things out, but sometimes that isn't good because it's making it, pretending that I'm drawing circles or something like that. And that last number is square root of 3 inside the normal CDF. So as you can see, this pretty much is built on top of the last type problem with the extra algebra, which is why it's much more likely that I would give you this type of problem than the last problem, because this problem does both this along with what we had in the last one. So any questions on this? So the next one is the last thing we did yesterday, which is, now I do want to use what's in parentheses there. If we have an option to buy stock for $60 in 4 years, how much should I charge for the option? So getting to it is kind of annoying, but we do get an equation here, just so you can write it a bit more simply. We write it in two parts, so there's going to be a b that we're going to first get, and then we're going to plug it into that top equation. So I get this. So the new things here, which we didn't use in the last equation, are capital K, which is the price we can buy the option for. So that's going to be the 60. And the capital T, which is when we can buy the option, which is the 4 years. So therefore, if I plug this in, I get natural log 50 divided by 60. A was 0.04. Sigma was 0.06. So squared divided by 2. T was 4. Sigma was the 0.06. Square root of the 4. So there's the preliminary little part. Even more so than the last one, definitely check my arithmetic here. So I'm getting that is negative 0.24. And here, if you want, you can rewrite this, which is, remember that this thing is whichever of those you want. And this last one, the normal CDF negative 1,000, comma x, if you have the pop-up window where it also asks for mu and sigma, this is the standard normal. Mu is 0, sigma is 1. So you plug those in. So I'll write it in that last one. So remote. This is the normal CDF. And as I said, this you should definitely be checking my arithmetic because you can see how many moving parts there are. That I get is $1.90. Little thing, obviously, if you get a negative number, something has gone wrong because it doesn't make economic sense for you to pay someone to buy an option. There's no way you could make money if you're paying someone to take an option. So a negative number here doesn't make sense. Oh, because if you look up here, that's this first part here. the sigma squared of t plus b. And in the second one, it's just b. So this is the solution to the Black-Scholes equation. And if you remember, just so you remember where this is coming from, this came from pretty much the same thing as our first example, which is we found the expected value for the stock, and we found the expected value for the options, which gave us one sort of basic equation and one an integral equation. And when we solved, we got this solution. Actually, solving is really tedious, so we don't want to actually do it every single time like we did the first problem. We want to have the general solution like I do here. So once we have the solution, it's a fairly straightforward, although kind of tedious solution. But any questions on this? Okay. So as I said, at least for a while, this was actually used in the real world. So unlike a lot of this stuff, it's something that's useful. Yes. So in some ways, that's what I'm saying here. Really, I should be using that notation because it is the CD, actually even better, this one. That's what phi is, the CDF of the standard normal distribution. So therefore, yes, mu is equal to 0, sigma equals 1. So as I said, in the newer TI that I got, when you do the normal CDF, it has a pop-up window and asks you to fill in the numbers. So you have to put in the mu and the sigma. So in that case, yes, you need that mu is 0 and sigma equals 1. Any other questions? Okay. All right, so let's kind of backtrack a little bit, which is pretty much since we stopped the statistics, we have been doing stochastic processes. So when we were doing Markov chains, a Markov chain is a stochastic process. When we then did the Poisson process, obviously that's a stochastic process. And queuing is built on top of that, so that is also. And now Brownian motion is also a stochastic process, because a stochastic process is just any sequence of random variables that depend on time. And pretty much all the ones that we've looked at so far have a simplifying assumption. So either they're independent, as I said, so the Poisson is strictly independent, so when we did the Markov chains, there wasn't independent, but it was kind of the next best thing, which is all I need to get the next where it's next is where it is now. For Brownian, the distributions are independent as long as there's no overlap. For stocks, we're assuming that the percentage change each day is independent. So all the ones we're assuming things are independent. But there's no reason that would be true. So for example, an electrical current is basically a stochastic process. At each time, the current is actually a distribution. It could be anything along a probability spectrum. And obviously, that rate at one time is going to be related to the rate at the next time. So in general, there's no reason that stochastic processes have to be independent. So here we just do a quick side thing, which is say, what other tools, what other definitions do we need if we don't make this simplifying assumption that things are either independent or close to it? So here are a few definitions that can be used, and we'll just talk about them with a particular example, maybe. That might happen Monday. So this obviously is nothing new. We can get the mean at a particular time. But now I'm going to give it a notation. And that's just the usual expected value. So that's not really new. This one is the autocorrelation. Is given by this. We sort of used the correlation when we were doing regression. Remember, this isn't quite, there are kind of two correlations. There's the correlation coefficient, which this is not, and then there's this correlation, which is e of xy. This part, so this is a correlation which somewhat came up in 3081. If you put the auto in front of it, auto just means you're going from one state back to itself. And so the reason it's called autocorrelation is we're using the same random variable just at different times. In the more general one, if you have random variables x and y, the correlation is e of x times y. Oops. In some ways, should have been obvious as I was thinking the other one. So that should be at R, C, because this is C. And this one I'm going to go, oh, I should be able to do it. And this also, you might have seen quickly in 3081, which is the auto again is just saying we're going from the same distribution to itself. If instead it was x and y, then it would be the covariance. And if you remember the covariance you use if we're looking at the sum of two random variables, the covariance of the variance of the sum of two random variables. And in that case, it would be x minus mu of x times y minus mu of y. And that simplifies to autocorrelation minus the product of the two means. And as you might expect, these are measures of how related the two variables are, or in this case, how related the random process is at two different times. In particular, if they're independent, so if the different times are independent from each other, this last equation becomes zero, and so it fall off, which is why we usually don't use it, because often it's zero. And this would give us what the distribution is, the joint distribution at different times, if the different times are not independent. So for example, if we are looking at electrical current, which is a Gaussian stochastic process, then to get the joint distribution between times, we need to know what is the autocovariance between two different times. So these would be tools that would give us how to get the joint distribution between different times. Okay, so let's do a quick example to see what we're talking about here. So this is a general, simple stochastic process, which is, it is a random variable, but it's changing as time goes along. So at time t equals 0, it's just the point 0. At t equals 1, it's just the distribution as given, 3a squared, and then as t gets larger, it's widening out, which we'll see in a second. And in this case, the random variable, the distribution at different times will not be independent. So let's see how far we get. So the first thing, which goes back a ways in some sense for us, is let's find the CDF. And we did this around the time we did regression. I'm trying to remember exactly when we did it. Oh, we do it the same way. So there's the definition of the CDF. We put in what x is. We then solve for it in terms of capital A, because we know the density function for A, which means we can now do this probability. So there's our CDF. And now, again, like we did before, we need to get the new sample space. And it looks different, but it's the same as before. What is the new sample space? So originally the sample space was A goes from 0 to 1. What is it now? So when A is 0, what is x? Remember what we just do is just plug it in. So it's equal to A times 0, which is 0. And when A is 1, if I plug that into x, I get t. So there's my new CDF. Okay. So this, in a different setting, with a slightly different notation, we've already done. Getting the CDF and PDF of a function of a random variable. pieces, and I'll probably just do this one and we'll continue it on Monday, which is now we want to find the mean at time t. And we have two ways of doing it. One way is this is the CDF. Given a CDF, how do you get the PDF? You just take the derivative with respect to x. Yeah. So if I take the derivative of that with respect to x, I get, however you want to do it, I can either break it up, it's x cubed over t cubed. So I can either, or I could use the chain rule. So 3x squared over t cubed. And then I know e of x, I'll ignore the t in some sense, is the usual integrate over the sample space, which is now 0 to t, of the x times the PDF. So that's one way of setting it up. The other way is we'd remember that, well, e of x is really e of x of t, and x of t is a times t. And so therefore, since that's in terms of a, I can use the PDF of the original density function, not the one we just got. And so therefore, our sample space is the 0 to 1 that we started with. And we have e of something, so we multiply that something times the PDF. And so that's 3a cubed, so we get and it better be that whichever way you do it, you get the same number. And we get our expected value in terms of t. So as you should expect, at time 0, the mean is 0. At time 1, it's 3/4. At time 10, it's 30 over 4, and so on. So the mean is getting larger as time goes along. So let me just set up the next one. But any questions on this? Obviously, we have to do more examples if it's going to be on the test. But any questions on this? Okay, so part C. So the autocorrelation is e of x at t1 times x at t2. And here we run into problems if we're going to try it the first way from the last part, because you can see we have two variables here, which means we need a joint density function. Well, we don't have it. In some ways, this is kind of circular, which is to get the joint density function, we're going to need either the autocorrelation or autocovariance, which we are trying to get. On the other hand, if I do it the second way, it becomes pretty easy. If I put in what x at t is, it's a times t1. X at t2 is a times t2. And now it's in terms of a. So therefore I do the sample space for a. I put in this, which is, I'll put the two a's together. It's lagging on me, so give me a second. So the AT1 times AT2. Multiply multiplied by the density function. So E of something is the sum thing times the density function. And therefore I get this. And you can see in this case, the autocorrelation will be in terms of T1 and T2. Actually, I said set it up, but this is really easy because it's just 3/8 of the fourth, so it's going to be 3/5 T1, T2, 8 to the fifth, 0 to 1. I get that. So as T1 and T2 get larger, the correlation between the two times gets bigger. And then I'm alpha finished off, sorry. And then the autocovariance is the autocorrelation minus the two means, assuming this is what we got in the last one. I think that's right. We get something like this. And that's not 0, which means that they're not independent. And so therefore, if we're building a joint distribution, we would have to include either the autocorrelation or autocovariance, depending on what the thing is. So these are the tools we would use if we wanted to find the probability that something changes from one time to another time, because I would need what is the joint distribution between those two times. And to get that, I need one of these two, the autocorrelation and autocovariance, which gives a measure of the relationship between the two times. So if we had more time, this is the next thing we would do, which is talk about what happens if things are not quite as nice as all the other ones we've done. So let me stop there. So what we'll do Monday is more examples of this, and then we'll decide if it's actually on the test, and that will tell me exactly how far the test will go. So I'll tell you what exactly is actually on the test, what sections and so on. As I said yesterday, the take-home will take a little while to grade, so hopefully I'll have it Monday, but don't count on it. I will put the answers up tomorrow, at least you know about how you did. So any general questions? So kind of the usual thing. Let me stop recording.